Show that the plates of a parallel plate capacitor attract each other with a force given by a force equals this. Prove this by calculating necessary work to increase the plate separation from x to x plus dx, charge of Q remaining constant. Okay, so I'm going to say work equals force times distance. Actually, I'm going to do it a little bit differently. Work equals F dot dx. And we're going to go from x to x plus delta x. And there's a couple ways of probably approaching this. What I'm going to say, and I'm not quite sure what they expect us to use for formulas and what we can kind of assume, but I'm going to say that force equals Q times E, where E is the electric field. And the electric field for a plane of charge, that's what that little line there is supposed to be a plane, is going to be sigma over 2 epsilon naught. Now, we can, I just have that memorized, and I'm assuming it here, but it can be derived using Gauss's law, or the whole idea of electric field, too many lines on that E, K, Q over R squared, electric field for a point charge, and then just doing a whole bunch of integrating and symmetry and a little bit of trig, and you can get the same thing too. So in this case, sigma is going to be, we're going to assume that these parallel plates, since a parallel plate is a conductor, all the charges are going to move out away from each other uniformly, and so we're going to get a uniform charge density. So we're going to get Q, which is the charge, over A, which is area. So this is going to be the same as Q over A times 2 epsilon. And I'll do epsilon naught. Difference between epsilon and epsilon naught is epsilon assumes a dielectric, epsilon naught assumes the dielectric is a vacuum, which is pretty much always true, and since they use epsilon naught here, I think that's what they're implying. Alright, enough background. Let's do this. Game face. So this becomes work equals integral F, which is QE, which is Q times, I'm going to write another small q here, because one q is from the left plate, the other q is from the right plate. So these are different q's, but they're actually going to be the same. That's kind of assumed with the parallel plate capacitors you have, it actually would be negative. But that just tells you the direction of the force. The idea is you have a battery hooked up to this, and you're providing positive charges to one side, negative charges to the other, so Q and Q. I'm going to leave off the negative sign, because that just tells us direction. And this could be Q over, over 2 epsilon naught times A. And then we're going to still have dx there. Well, the nuance here, or the little caveat that makes this a lot easier, is that these are all constants. So this is going to equal q squared over 2 epsilon naught A integral dx. And then we're going to get, when we do the when we do this, we're going to get q squared 2 epsilon naught A times x plus delta x minus x. The x's cancel, and we're just left with delta x. This delta x is the same as d, the separation between the two plates. And so work, which is force times distance. Yes. Is that what we're looking for? Let's see here. Yeah, I'm going to say work is force times distance equals, and that's for uniform force, which we have here, q squared over 2 epsilon naught E A times D. The D's cancel, and we're left with force equals Q squared over 2 epsilon naught A. And they might have had a different idea of how we're supposed to solve this, because the whole part of doing work was kind of just superfluous and superficial here, because the whole work is meant, well, multiply by D and multiply by D and then cancel it out. So they might have had a different idea of how they wanted us to prove that, but we got the answer, Q squared over 2 epsilon naught times A. All right, so then for part B, we want to use the result from part A, and we want to show that the force per unit area acting on either capacitor plate is given by 1/2 epsilon naught E squared, which is known as electrostatic stress, and the result is true for capacitors of any shape. All right, so electrostatic stress kind of makes sense. So stress is basically the mechanical equivalent of pressure. You've heard of like stress strain curves, basically how much a metal deforms based on how much you're pulling on it, and that stress is measured in force per unit area. So this is a force per unit area, which is same dimensions as pressure. This is basically the pressure due to electrostatics. So electrostatic stress as a word seems to make sense. So we want to show that the electrostatic stress, which is force divided by area, same as the pressure, is going to be our force, Q squared, I'll write a little B here so we know we're working on B, Q squared over 2 epsilon naught A, because that's what force is, times 1 over A, because that accounts for that divide by A right there. So we want to write this in terms of E, electric fields. And to do that, we're going to write out what the electric field is for the parallel plate capacitor. So before, I wrote this down and I said electric field for a parallel, for a plane is sigma over 2 epsilon naught. I'm going to write that as Q over 2 epsilon naught A. Q over 2 epsilon naught A. Now the trick here, because it's easy to get confused about that 2 in the bottom. So we got 2 plates here, and this one's going to be positive, this one's going to be negative. What this formula says is the positive one is going to create electric field lines going outwards. And that's going to be defined by this equation. The left plane, which is negatively charged, is going to create electric field lines going inward. And so what happens is, outside of this parallel plate capacitor, the electric field lines oppose each other, so they cancel out. Same on the left side. Electric field equals 0. But inside, they're going to reinforce each other, because you can see the positive is going from right to left, and the negative plate is also causing electric field lines to go from right to left. So then what I would write is electric field with 2 lines, parallel plate capacitor, is going to be 2 times this, which is just Q over epsilon naught, times A, area. And that's really the trickiest part of this, is just realizing the difference between the electric field due to a single surface charge and the electric field due to a parallel plate capacitor. Another time you kind of see this concept play out is like if you have for some reason you have an induced charge or something, and you have like a charge on a conductor, and it says that the surface charge density, sigma, on one side is this. Well, if it's a conductor, that means you're going to have the same surface charge density on the other side, and you have to treat this as 2 separate planes, which is why you're going to use the Q over epsilon naught A and not have that 2 to divide it by. So that's just something to keep in mind in life. All right. So we're not as concerned, though, with electric field as we are concerned with electric field squared. So it's going to give us Q squared over epsilon naught squared area squared. Plugging this into our equation up here. Actually, I'm just going to solve this then for q squared and see what happens. So q squared equals epsilon naught squared area squared times e squared. There we go. Looking at this equation we have up here, plugging it in down here, so we get force divided by area, which is our electrostatic stress, electrostatic pressure. It's going to be epsilon naught squared, area squared, electric field squared, which is the same as q squared, all over 2 epsilon naught, and I'm going to say a squared because we have an a and an a. From there, we're going to cancel the area squareds. One of the epsilons cancels, and we are left with epsilon naught e squared over 2. Let's see if that's what we want. Epsilon naught e squared over 2. Epsilon naught e squared over 2. Bam. Got it. So that was how we did that part. So this one, conceptually, not that deep, but it's easy to get confused. The biggest trick is just either knowing or knowing how to derive the formula for the electric field due to an infinite plane. Again, that could be either Gauss's law, or which is the easiest, or to go through basically view everything as point charges, and then integration trig and such. So, and the thing is, it's uniform from one plate to the other. And then when we did for the parallel plate capacitor, we have to know that this is the formula for one plane, and then this is the formula for 2 planes, which is just double, but it looks weird because it's like, oh, they forgot the 2. No, they did not, because it's doubled up. So, hope that helped. See you next time.